Bueno, hoy tenemos la visita de Cristian Guillermo de la Universidad de Bergen. En particular es director del Instituto de Energía Eólica Offshore. Y hoy vamos a hablar sobre un problema estructural. Muy interesante porque Cristian hace un par de años ganó un Consolidator Grant de Geophysical. Y entonces sería muy interesante encontrar fuentes de colaboración entre la Universidad de Bergen y... Así que también con los ojos abiertos y los oídos atentos para ver si se puede colaborar en algo. Gracias, Cristian, por visitarnos.
Bueno, muchas gracias. Voy a hacer la presentación en inglés. So I'm quite happy to be here, first time in Chile, in Barcelona, and I hope it's not going to be the last. So today I'm going to have a talk about numerical analysis of slender structures, methods, and application. This presentation is comprised really by two parts, but I added another part to tell you a little bit what I'm doing right now, more at the administrative level. So, yes. So basically, I would like to tell you some minutes about the Bergen Offshore Wind Center. So the Bergen Offshore Wind Center is a research center on offshore wind energy at the University of Bergen. And what we are trying to do is to develop a new knowledge for the sustainable development of offshore wind energy. And we have a vision, and the vision is in some years from now, all the decisions to be made within the field are going to rely either in our methods, our methodologies, and our tools. And for this, we are identifying challenges and opportunities within the field. Also, it's important for us to carry out excellent research, and we would like as well to become a leading communication hub. Basically, the Bergen Offshore Wind Center is located at the Geophysical Institute, and this is where we started with this topic. So the topics that we are dealing with are of geophysical nature, for example. So we would like to characterize the resources we have, but also we know that this should happen in a given context. So we need to understand the impact that we are doing to environment and to society. And also before you start installing wind turbines, you need to have rules, regulations, and so on. And what is based on several documents at the Norwegian national level, but also the European level. So why our center is a little bit unique? So myself, I'm a structural engineer with a background in computational mechanics. But now if we would like to develop offshore wind energy, we need much more than that. And the concept is that in our center, we are dealing with things that are surrounding the wind turbine, and we consider them all equally important. So we would like to combine knowledge in marine ecology, also geophysics, this is meteorology, oceanography, and marine geology, also social sciences, legal sciences, and we have a lot of phenomena going on, and we would like to take this information into account. So many data, and we have data that is of, we can label as a hard data, so the wind velocity, the mechanical properties of the soil, but we have also the opinion of people, and this is something we call soft data. So the idea is to use this information to take decisions, and this is something that we are working on to allow this. And we are convinced that the future of offshore wind energy depends strongly in carrying out multidisciplinary research. So a little bit of the center, we have more or less 44 people working in the center. 20 of them are professors and associate professors. And then we have more or less 25 PhD students, also researchers and postdoctoral researchers. And currently we have a project portfolio of 156 million Norwegian crowns. In euros, you have to divide by 10, and this is more or less the budget we are relying on. And as this is a new center, we started in 2019, and I took over as director in January 2023, where I started to generate publications, reports, and so on. So we are growing, we are becoming better, but however, we are still starting with the center.
This is a public center, private?
It's a center that is located at university.
So you don't have a VAT number?
Not yet. No.
It's a university.
Yes, yes. Okay, so now I will like to move to the more technical part. And this is something that I always say, and this is that it is important to work with methods and with applications. If you only work with methods, you will lose, connection with reality. And if you work with application, there is a big danger that you are not using the best method to solve your application. So you need to try to do both at the same time. And something that I did in the last years is to work with structural analysis. And basically, the kind of formulation that I'm using is this variational statement we have here. And you can see here that we have terms that are due to, for instance, the second one is the equilibrium. We know the first one is the match of momentum when we have a dynamic system. Then we have additional terms when we use mixed formulations, three-field formulations, whatever. And also we have additional terms because we are also going to deal with constraints, and this can be holonomic, non-holonomic, and so on. So we need to have a framework that is general enough. And basically, my expertise relies on using three kinds of canonical models. So basically, beams and shells, but the rigid body is a very rigid concept, and basically what you do is you start with the rigid body and then you move further. In this kind of formulation that I'm using here, I'm not using rotational degrees of freedom. So what I'm using is directors, and I'm describing orientations with these directors. With this setting, what we can warrant is having objectivity and path independency of the continuous and the discrete formulations. So you have your continuous formulation, and then you apply the finite element method, and then you obtain formulations that are well behaved. So, basically, when we have these kind of formulations, it is important to be sure that this is working well. And for instance, with the static analysis of this kind of a structure, this is a ring, we apply a moment and then we perform the deformation, and we can see that the load factor versus the displacement are developing a trajectory. And when we have this kind of formulation I'm using, the trajectory is always the same. But when you compare with other approaches that are based on updated Lagrangian formulations, they are compromising these properties. Of course, it depends the application you have. So if you want to simulate punching processes, you don't need this kind of setting. But if you are simulating wind turbines, after many rotations, you are going to have information that is not right. And with this kind of formulation, we avoid having these issues. This kind of formulation can be also extended to general cases. So here we have a shell, and we release the shell to move and deform. And we can see here that with this kind of methods, we can preserve linear momentum, angular momentum, and also energy. But shells are very prone to have high frequency content, and this can blow up the simulation. And something that we can add is dissipation. But dissipation is good, but we need to do always very carefully, because we don't want to spoil the solution for our system. So here we also can formulate dissipation functions that can mitigate the high frequency content. As we are having a nonlinear system, it's not like in the linear system that you can separate all the frequencies. So here we have the theorem for equipartition of energy, and after some time we are going to distribute the energy across all the frequencies. And this is why these kind of nonlinear models are very delicate. So other kind of problems that I am working with, also within this framework, is with the so-called Kirchhoff rods. I don't know whether you are familiar with this kind of formulation, but basically there is no possible to derive a primal formulation. So because these constraints, non-shear constraints, are not integral constraints. So you cannot have a primal formulation and you need to have a primal dual formulation. But if you consider some simplification, for instance, a symmetric cross-section, and also that the rod is initially straight, then this is the only case in which you can develop such a primal formulation. And this is what we did a couple of years ago. Basically, our motivation was to investigate mooring lines for floating wind turbines. But this is something that you can use for bridges, or if you have a rod, you can use this kind of formulation. And then something that we can see here is that we have the formulation, the geometrically exact formulation, which is basically a generalization of Timoshenko, in which we have shear deformation. And you can see if the shear constant is low, you can see that the vector that is perpendicular to the cross-section is not tangent to the mean line of the beam. If we are increasing this factor, we are going to see that this model is converging to the solution provided by the Kirchhoff law. In this case, what we have is a nonlinear model. And to formulate this model, we need to rely on concepts from differential geometry, because we cannot use anymore the standard concept of curvature. And it makes a little bit delicate also this model. And when we started to investigate the convergence property of the geometric exact beam towards this model, we realized that at the beginning, we had some kind of linear convergence, and after that, we have some saturation. And basically, what we did is we went back to the linear model, and then we started to investigate what happens. And this behavior can be explained from the analytical solution from the Timoshenko beam and also the Euler-Bernoulli beam. And also, the difference what you have here with respect here is that here you have the nonlinear model, so you cannot decouple the motion of the structure. So, and here, basically, we have only the flexural component of the solution. And therefore, you can see this peak here, and this peak you don't observe here because when we have this kind of situation, the axial part is dominating, therefore is masking these peaks. And also, the position of these peaks also depends on the discretization. So when this edge of the structure is getting smaller, then these peaks are moving toward the right. So basically, with this, it gives us a good idea that the model is working properly. Then also, you can use this kind of model for doing dynamic simulations. And you can use this for DNA simulation. You can use this for spaghetti simulation. So there are many things you can do with this. And basically, we have this model in which we apply some symmetrical condition to make the system to rotate and deform. And we apply this for the geometric exact beam and also the Kirchhoff rod. And we saw that after some times, the trajectories are different. And are not different because of artificial numerical aspects, it's because the models are different. Then other thing that we can do with this is, as we are not using degrees of freedom, rotational degrees of freedom like angles, we are using directors. Basically, we are relying on Severo manifolds like the unit sphere and the SO3 manifold. And what we have here is basically, in the first case, we have a shell pendulum that is allowed to move, yeah, like a pendulum, but it's a 3D body. And the idea was to try to investigate whether we can find paths of motion. But you know, basically what you do when you have this kind of problem, you apply, for instance, model analysis, and then you have your modes, or you can apply POD. But do you know why we cannot do this with this kind of structure? Because the configuration space is not a vector space, it's a manifold. So you can use POD, principal component analysis, model analysis only when your space is a linear space. In this case, we are dealing with manifolds, so we don't have that structure. But something that we can do is if we have the trajectory on the manifold, we can define a point, a tangent plane, and to do a lift of the trajectory. And then in this plane, we can carry out principal component analysis. Once we identify the modes, we can reconstruct the trajectory and we can project back to the manifold using the exponential map. And this is what this is about. So here you have the manifold. Here we selected one point, and this is the trajectory that we have in the tangent plane. And here we have two experiments. The first experiment is we compute the trajectory, we do the lift, and immediately we project back the complete trajectory. So only doing this lifting and projecting back, we are destroying the preservation of energy because of numerical artifact. So you can see that the green one, we have all the terms, so we are not truncating anything, but we are losing energy, or we don't have an energy that is constant. Now, what we did is, we did the lifting, then we carry out principal component analysis. We took a number of modes, and then we projected back. And it's important to know how to identify the number of modes you need in order to reconstruct your solution. And what we are doing is we are taking a look to the singular values, and we observe when we have a jump of an order 10, and then we take up to this jump. And you can see that if we do the projection of this, the projection back of this truncated solution, you can see that the energy behavior is quite good. Now, if we take less terms, we are going to see that we are affecting the energy. So we have a worse quality of the energy when we do like this. But clearly, in this case, we have this shell pendulum is a 3D problem, but it's happening mostly in a subspace, which is a plane. But now, the free-flying plane we saw is rotating and moving and so on. When we see the sphere, we can see that we have points everywhere. And now we do the same. We identify one point, then we perform, we take the tangent plane associated with this point, we do the lift, PCA, and back again. So you can see here, again, we did with the complete solution. We also have some problem with the energy because this numerical artifact. And then we also play with truncation. Yeah, so the 295 is we identify when we have the jump, and then we took all the terms up to this jump. And for 222, we took a smaller amount of terms. And we can see that here it's quite clear that we are degrading the energy behavior. So the idea of this is we would like to use these techniques to solve or to analyze real structural problems. And the idea was to apply this technique to offshore wind turbines or onshore wind turbines as well, and to try to use this technique for structural health monitoring. Because if you have a wind turbine, you have a blade, and what you can do is to try to follow the frequencies of the blade. But as soon as the blade is rotating, you are going to have a geometrical stiffening, and then the frequency is going to go up. Then it's not happening anything wrong with the blade, but the blade is rotating, and you have the term coming from the geometrical stiffness. So you cannot rely on observing the linear modes for saying something about that structure. So, and then what we did is we applied this technique to try not to do a structural health monitoring at the first, but at least to try to see whether we can recognize some structure, abstract structure in the motion of the wind turbine. And this is what we did for a wind turbine. And you can see here, we did the same analysis. So we did a simulation with the wind turbine. We did the lift. We compute all the singular values. And then we projected back. Then we also concealed this with a reduced number of modes. And then also a very extreme reduction of modes. And you can see the behavior of the energy is consistent with what we saw in the simplified cases. And here what you can see is the directors. These are the vectors compressing the triads associated to the structure. And you can see, for instance, for the director in one direction, in the other one, and in the other one. And then here, what we have is the representation in the Lie algebra. So these are different ways of observing this process that is happening in a manifold. And we are identifying a structure, and this is, I would say, an interesting starting point, and we would like to work further in this direction. And a potential use of this technique beyond structural health monitoring is also for model order reduction. So, but this time we have models that are non-linear, so we need to be very careful how we are doing the model order reduction. So to finish the theoretical part, something that is very popular nowadays is everything is data-driven, data-driven that, data-driven this, and so on. And you know, it's not clear what data-driven is. So basically, what I'm doing, I am following this paradigm developed by Miguel Ortiz, data-driven computational mechanics, and I am applying this to structures. So here we have a case. This is a building made of wood, and you know that wood has very good properties, but are different from more standard materials we know. And the thing is, we have a structural idealization for our structure, and then we also have data. And in the rest of the cases, what we are having is something like this. But this is quite optimistic. We are going to have something more like this, or even worse. But basically, the assumption of this paradigm is that we have a constitutive manifold, and we don't need to have the energy structure. We have just a manifold that is relating stress and strain. And I am going to say this in a very mathematical way, but what is measuring? Measuring the constitutive manifold is basically we have the manifold there, and then we touch a point of the manifold, then we systematically add noise, and then we project this in a space of a lower dimension. And this is what we can measure. So we never are measuring the complete, all the components of the stress and the strain tensor. So reality is even more complicated than that. But the question is, it is possible to relate this kind of setting with this kind of setting? And the answer is yes. And basically what we can do is to define an optimization problem with the following structure. So we are going to minimize a cost function in which we look to minimize the distance between the internal state of the system with respect to the data we have. So we have here in the second line, we have the data that is a data set. We have a finite number, as much as we want, and we can have, but a finite number. And then this equation we have here is basically the equilibrium, the compatibility, and also additional constraint that we can have. And this problem is a very difficult problem. And you know why? So this is a discrete continuous optimization problem. So we have variables that are continuous, the displacement of the structure, the strain, and the deformation, the fields that we know when we solve the PDEs. And then in addition, we have the information coming from the experiments. And we have finite number. So this is a non-smooth optimization problem, and is a problem that can be classified as NP-hard. It means that if we have a solution, we need polynomial time to check whether this is a solution. So here I have a concrete example. But basically, what we have here is the simplest cost function that we can minimize. So basically, we are having here the norm 2 that we are minimizing with, and then we have here stress strain. Basically, this is a explicit function of the stress as a function of the strain, and then we add some perturbation, but we can have something else. So these are two possibilities. And now when we are dealing with metamaterials and all these kind of new possibilities we have, something like that can arise. But we need to have formulations that can take into account this kind of situation. Then what I did here, I solved this problem. Basically, I evaluate this cost function for all the points and different load cases. And what you can see is that the cost function looks like this. And if I ask you, do we have a minimum? Such a thing like a minimum doesn't exist anymore. There are ways to try to say more about this. And this is something that we are developing right now. But it's a very complicated problem. So if this is so complicated for 1D, you can imagine if you have a wall structure and all the components of the strain and stress tensor and so on. So this problem has a very rich mathematical structure. And if you understand well this mathematical structure, you can simplify this calculation and you can obtain results in times that are not that short as the ones that we need to solve the PDE, but times that maybe 2 or 3 times more expensive. And this is ongoing work right now. So then I'm going to move to a second part, more on the applications. And I'm going to start with the typical torsion problem, the working functions. So, you know, blades are made with composite materials. And then when you are going to fit your aeroelastic models, basically you are modeling pins. So you need to have properties for the cross sections. And this motivated us to take a look on that because for if you have composite materials and also you have a complex shape, multi-cells structure, it's not that easy to determine the warping function. And this was a little bit of theory, but also a little bit of a practical work. And then we realized that when we analyze warping, what is the common practice in engineering? What we do? So we have a problem that is a problem that has natural boundary conditions. So what we need to do is to fix a point. But the practical approach is we fix a point to be 0 and then we solve. Yeah? So this is something that works and works well. However, this kind of approach has no counterpart in the continuous setting. And then this triggered for us to investigate how to formulate this problem properly. And we realized that there are basically 3 kinds of formulations. The first formulation is to look in a space, look solutions in a space with average 0. The other one is to impose the constraint with Lagrange multipliers. And the third one, very good old friend, who use some kind of penalty approach. And basically, this problem, you can prove analytically that these problems are totally equivalent. So you're finding a solution, it's the same solution, and you can go back and forth. However, the numerical implementation might differ because of conditioning issues and so on. And for instance, if you use the penalty, the problem, what you are doing is you have your stiffness matrix is singular, you compute the null space, then you have a vector, and with this you stabilize this null space, and you use a penalty parameter. So you are adding a stiffness. And depending how you choose this penalty parameter, you can modify the condition number of the overall matrix, stiffness matrix of the system. And this is something that you have to do carefully. However, the quality of the solution is independent of this parameter. So, and now, once we deal with that, we also realize that, coming back a little bit to the previous slide, that what happens if you fix the information in one point? So you have your finite element model, you fix it, and then you solve the problem, you're going to get a solution. And this solution is consistent with these approaches that we have here. But if the discretization is going to 0, then there is the trace. You have the trace operator that allows you to extend information in the boundary into the interior field. When you have, for instance, a gap of dimension equal to 2, the trace operator is no longer bounded. So basically, you have no theory to deal with that. So you cannot find a limit case for this approach. Also, probably it's not new, it's known, but we didn't find many contributions in this regard in the literature. So once we have this working, we try to investigate different situations we can have. So let's consider a section in which we have two materials. And then what we did, we play with the different materials with different coefficients. And then we observe here how this is modifying the solution. So here, when the quotient of the materials is equal to 1, we are going to see that we obtain what is usual. This is the symmetric behavior, and here we have the antisymmetric behavior. But when we have a different radio, what we are going to observe is that we have perturbation. Yeah? And then something that is very important in civil engineering when you compute bridges, when you have loads acting on the bridge, is to know how the bridge is going to deform the cross-section. And this is a benchmark that is also well established in the community. And we checked this methodology, and it's working as expected. Then another application is mooring lines. This is cables immersed in water. In this case, what we are considering here is a cable of aluminum, and we have water at rest. And we apply on one end, in the free end, we apply the vibrating force. And we give as an input the amplitude and the frequency. And we realize that when we have a frequency that is higher than a given frequency, we are going to get this shape, and the structure is going to remain like this, like an L. And at the beginning, we thought that this is only of academic nature, but indeed, this also can happen if you have marine installations. The setting is different because basically you have the anchoring system here, and the pulsating load is coming from the free end on the surface. But this behavior is something that we can observe. So, and you can see here this frequency. This is the subcritical behavior, and this is the supercritical behavior. And then here is basically when we have the mooring line here, we have force that is tangent to the mooring line and force that is orthogonal. And among all the forces coming from the fluid, we can identify the added mass. We have the tangential drag, and we have the normal drag. And we can see that for subcritical frequencies, the normal drag is the dominating one. But when we move towards the subcritical regime, what we can see is that the normal drag and the tangential drag are equally important. And this is something that you can see in the plots for the displacement. So you can see in the first one is for the subcritical behavior, and the second one is for the supercritical behavior. Yeah, so basically we have models for the structure with slender structures or beam shells and so on. And we need, when we compute wind turbines, the dynamics for wind turbine, we need loads. So I'm not that good with flows like you, Sergio. So I am applying a very modest flow model that is a boundary element method. And this method allows us to compute the loads in a good way, and also to compute the wakes. And basically, this method works well for wind turbines when you want to compute loads. But if you want to compute more details, you need something better for sure. However, this is also cheap enough. So you have engineering approaches in which you need seconds. This kind of methods, you are talking about hours, and if you go to CFD, we are talking about weeks or months, I don't know. And we can investigate several phenomena. And also in this model, we have several things applied in order to have more reliable simulations and also faster simulations. So we have particles, and we have also diffusion models. And we are doing the work now to compute this with the fast multipole method. And this is going to be even cheaper. And then you can see here, in this plot, we have the mechanical power of the wind turbines. And for the first guys, what you have is black and blue. So this is the one that is on the front, and this is the one that is back the first wind turbine. But if you change a little bit the yaw, you are going to see that the gradation of power is going to be less. However, we have some oscillations there, and these are caused because of the interaction of the wind turbine with the wave. We suspect that also we have here a numerical component. You know, boundary elements are basically singularities. And when you are too close to singularities, your solution is not that reliable. And the idea of this setting is to apply this, for instance, to a bridge or to a wind turbine. And this is what we did. And we have, this is a model for a bridge, an elastic model. And then you can see we compute the vibration. So we have a geometric exact beam. So it's a nonlinear beam model that admits shear deformations. And then in gray, we have the aerodynamic mesh. And then what we have behind is the wave. And something that we can see is that this structure is reaching something called Lyman cycle oscillation. So you remember the Tacoma arrow. So when you go to physics, they say, oh, this was resonance. No, this is not resonance. So this is flatter because the wind is blowing at a constant speed. There is no pulsating or oscillating load. So, but this is an interaction. So when you are below the subcritical condition, the flow is taking energy from the structure. When you are in the critical condition, the balance of energy is zero. And when you're in the supercritical condition, the flow is adding energy to the system. So something I would like to comment to this is we are having here a fluid structure interaction scheme that is strong. And if you like to investigate this kind of non-linearities, you need to have a strong interaction scheme. Otherwise, it's not going to work well in general. And something we did in order to improve the robustness of the method is to compute the linearization of the dynamic model. It's a tedious work. So there is no big scientific innovation there, but it's a tedious work. And we did it and we implemented, and we are obtaining with the fluid structure interaction scheme quadratic convergence, which is quite weird. So I'm not familiar with many fluid structure interaction schemes that converge quadratically. But the reason is not the convergence in itself. The reason is because it's more robust. So when you are in a nonlinear, when you are going to a nonlinear phenomenon like flutter, if you don't have a strong interaction scheme, basically what you are going to observe is that the flow and the structure are divergent. So probably you're not going to get a solution. And with this kind of a scheme, this is working very well. So they are working together well. And something that we are doing is we don't need to have this strong all the time. So what we do is when we have some situation in which the changes are not that big, we use some kind of, this is still strong, but we don't use the full linearization, we use partial linearization. Then when we enter in this kind of phenomenon, what we do is we turn on the exact linearization for the fluid. And this is giving us a lot of robustness. And then we apply this also for wind turbines. Here again, we're using geometric exact beams. We're using momentum preserving, energy conserving, or energy dissipating algorithms for integration in time. And these are also quite efficient in, these simulations are cheap, I would say. And here you can see the angular velocity of the rotor. Here the rotor is free to rotate. We are imposing nothing. So, and then we can see here the mechanical energy. So this is the energy coming from the structure. So the elastic energy and the kinetic energy and the kinetic energy of the motion. So this is also having a very good behavior. And for us, what is important is the long-term dynamics. And then this is something that we are now starting to investigate. And I'm not very familiar with neural networks, but I think we need to give a try and to see, but we need to use this carefully. Not as a black box, we need to try to understand what is going on. And the idea was to apply these neural networks to investigate the ability to predict nonlinear phenomena. And this is the classical flutter diagram. So you have here the velocity, then you have here the amplitude of motion, and then what you have here is a bifurcation point, and then you have the supercritical branch, and then here the unstable supercritical branch. So, and basically here you are going to have dissipation, here you are going to have a Diamond cycle oscillation, and here you might have a different behavior. But the idea was to investigate whether we were able to deal with this. And basically what we did is we took two models, basically the structure is the same, but we are taking a very simplified model and a little bit more sophisticated model. And we did the training and we investigated the statistics and the performance of the different neural networks. And basically, if the neural network is not complex enough, you are not going to capture the nonlinear phenomenon. So the neural network worked well with the Fang model, that is an analytical model, but for the unsteady vortex lattice method, the performance was not that good. And after some velocity, we observed that the predictions we obtained with this setting were not good enough. So now we are starting to learn how to deal with this, and we are starting to investigate different topologies for the neural network. And then something I would like to show you as well is if you have good models, you can use this model for different applications. And this is what we are doing with these Kirchhoff rods. And here what we are modeling is through the structural interaction in generalized Stokes float. And we have, in these two cases, we have linear flows, but nonlinear structure. And here we have nonlinear flows and nonlinear structure. And you can see in this one, we have shear thinning, and in this one, we have shear thickening. And you can see that this guy can swim faster and longer. So basically, this is the motivation. Pay attention of the models, try to develop good models, and sooner or later you are going to find many applications. I don't like this kind of models that work well for a single application. Sometimes we need to deal with that. It's okay. But let's try to do it a little bit better. And something I would like to comment you is I'm not only dealing with computational mechanics. So this is an example of multidisciplinary research. And this is a satellite image of the German pipe. And you can see all these black dots, white dots you have there. So basically what we have here is the velocity field. This is a satellite image, and you can see the wind turbines in these white dots, and we have the wakes. So the wakes do exist. Yeah, and the wake is, there we have basically less energy. Yeah, and the form of the flow is not the optimal that we need in order to harvest energy from the wind. So the thing is, when we are designing wind farms, it is very important where we are locating the wind turbines. And if in one place we have one operator and in the other place we have another operator, maybe there we can have a problem because one can ask for compensation because you are stealing, the wind. So, and this is a situation that is that we have in Norway. So here is the border between the waters belonging to Norway and belonging to Denmark. And we have this field called Ochoa 2. And here, this is the first zone that is going to be developed in Norway for offshore wind energy. And it's very close to the Danish border. And I don't know whether you know, but regarding energy, Norway and Denmark, they had some issues in the past. And before having this kind of problems, it's important to try to understand how to solve this problem before it arises. And from the fluid mechanics point of view, it's extremely complex because we are dealing with large scale, we have turbulence and wind profiles, and we have everything there. However, the big problem is not in the, I would say, the technical or the physical side. The big problem is in the legal side. So something we did is with some geophysicists, lawyers, and myself, we wrote a publication trying to formulate this problem with some kind of physical argument and then moving from the physics to the legal part. And regarding the legal part, is quite complicated because you have two figures, basically. Living things, this is fish, and non-living things, this is oil and gas. And wind is neither nor. So there we have some kind of legal vacuum we need to understand, to try to understand. And this is not going to happen in this field, it's going to happen in several fields in Norway. And this is something that is going to happen in other places. So there is something similar between Belgium and Netherlands, also Germany with other countries. So this is going to happen. And the interesting thing is that, this newspaper from UK, the Bergen, they wrote an article about this and they are citing our article. So I am quite happy for it. Yes, and then just to finish this presentation, I would like to present a last slide about my project. 1 year ago, I got this ERC Consolidator Grant with the title Data-Driven Offshore. And here, the idea is to use this data-driven approach, not the one based on neural network, the first one we saw in this presentation, to the elasticity of offshore wind turbines. And the idea is to integrate the data into simulations. And with this, we would like to improve the predictive capabilities of our simulation setting. And something that I would like very much to do is to create digital twins that are, I would say, well-defined from a scientific point of view. Because nowadays, digital twin technology is much of a business model for big companies. And the idea is to use this real twin and the digital twin and to use this data-driven computational approach in order to exchange information. And yeah, so something I would like to comment is we are recruiting people. So if you know some good candidates for a PhD position, so we have an open vacancy now. And in the coming 1 or 2 years, we are going to have another 3 positions. Yeah, so I think that is everything from my side. So thank you very much for your attention.
Question?
What's the profile of the researchers in your institute? Because you have presented a number of methods that are quite, I would say, advanced in the structural mechanics field,
Yes. This is basically my research.
This is only
my research.
This is your research. And do you have the counterpart in the institute? Do they have people that know about this? Are they familiar with this sort of would say consistent, exact broad solutions and this vector? Dr. Ubaki, his thesis also in this vector-oriented manifolds for shells. So the question is, do you have a group on that, or is it just you?
No, I have a group. So I started in Bergen exactly 3 years ago,
okay,
and I am building a group.
Okay.
So basically, we have the center in which we are trying to combine geophysics, geology, informatics, physics and technology, biology, law, social sciences, and now we are incorporating psychology.
Yeah, that's fine, but you find that you need some experts.
Yes.
And in the field you mentioned, this is a very, specialized.
Yes.
And sometimes, for instance, we have people here who come and do this on data-driven. They don't know anything about mechanics.
Yes.
There is a danger.
Yes, of course.
The question is, do you have more experts on
yes,
this?
So it's
hard computational mechanics.
Yes, when we are in Bergen, we have the Faculty of Mathematics and Natural Sciences, which I belong to, and we have a group of applied mechanics, and they work with fluids and also with solid mechanics. They are quite good in porous medias, finite elements. They're quite strong, but they are mathematicians.
So this is not useful.
No, but they are
so useful.
But what they are doing, we have a very strong connection with the oil and gas industry, and they are using basically the models that they are creating to explore the reservoirs. So this is something that they are doing. Also, they are doing carbon capture, storage, hydrogen. So they are not structural engineers. So they are mathematicians with a good background in mechanics, but it's more of a more theoretical nature, I would say.
Now, basically, the summary of my question is your center an integrator of knowledge, or you are developing new knowledge? This is the key question. New knowledge, new, I would say, basic knowledge. I think that your center is more like an integrator of knowledge. Is that
so at the center level, I am working as a sort of integrator.
Okay.
But basically, what I'm doing is 50 and 50. And when you get an ERC, you need to say, I'm going to work this amount of time, and I'm taking this seriously. So,
great. So, thank you.
¿Pregunta? Bueno, Cristian va a estar acá hoy y mañana, así que si a alguno le interesa reunirse con él y hablar un tema, seguramente podrán encontrar el momento.
Sabes, Cristian, que España también es uno de los actores importantes en la eólica, ¿sabes?
Sí, claro.
Tenemos un grupo aquí que está trabajando y una empresa, como ya se habla con ellos, nos interesa mucho esa colaboración.
Sí, mañana.
Sí. A ver si la transformamos en
realidad.
¿eh?
Sí, muy interesado.
Nosotros, ¿sabes? El logo de CIME era ¿cuál? From Knowledge to Solutions. Generating Knowledge and Solutions.
Sí.
Ese es nuestro logo.
Sí, yo creo que es muy importante. Por eso la presentación esta es métodos y aplicaciones. O sea, los métodos por sí solos, o sea, están muy bien como un desafío personal. A mí me gusta mucho la matemática, publico mis trabajos en revistas matemáticas, pero a mí también me gusta resolver problemas concretos. Entonces yo creo que ahí es muy importante y bueno, y eso también lo que está pidiendo la industria, porque energía eólica, la energía en general depende mucho de la tecnología, y bueno, hay un montón de conocimiento que está ahí, que no está usado, y hay que tratar de transformar ese conocimiento en innovación. Entonces, creo que hay que arrancar con los métodos, de las aplicaciones y innovar.
Y te contarán que nosotros estamos con la industria naval, que está transformándose en naval eólica. Los constructores de barcos construyendo plataformas offshore eólica, y te contarán que, o sea, que yo creo que
Sí,
si lo sabemos hacer, hay muchas oportunidades.
sí, sí.
Aparte, hermanos argentinos también.
Muy bien. Muchas gracias.